So one question you might have is, does this actually work? If I take a message and encrypt it, and then I decrypt it, does it actually work? A little bit of algebra should help us convince that it works. When you encrypt something, you take the key, XOR it with the message. When you decrypt it, you take the original ciphertext, which is K XOR M, there it is, and you XOR it again with the key. And remember that handy property from before where we said that if you XOR something with itself, it cancels out? That happens right there. So using our handy property, these two Ks cancel out, and you're left with the original message. So this little algebraic proof helps us convince ourselves that one-time pad does the right thing. Next question we should have is whether or not one-time pads provide security. So this one's a little bit fuzzy, and the reason why is because the INDCPA definition that we spent a lot of time coming up with last time, it doesn't fully work on one-time pads for the reason that in INDCPA, we usually use the same key through the whole game so that Eve can say, encrypt this, and then Alice faithfully encrypts it with the key. In this case, since we're changing keys every single time, the game has to be modified just a little bit to work out, but we can still show that one-time pads provide some level of security. So let's try and do that. So this is how I'm going to prove that one-time pads offer security. It's a little bit different from the INDCPA game because of the fact that the keys change every time. So you don't have to think too hard about INDCPA right now. But here's a mathematical proof that shows you that this game is secure no matter what Eve tries to do. Eve can invent new things we've never heard of. This game will still be secure. So the reason why it's secure is because we're going to consider the two different worlds that we can be in. So let's say Eve knows, kind of similar to the NCPA game, that either M0 or M1 was encrypted. Alice either encrypted dog or she encrypted cat. And we don't know which one she encrypted. So in other words, we are in one of two possible universes. In universe 1, cat was encrypted. And the message that was sent out was K XOR cat. In the other universe, the message encrypted was dog. So the ciphertext that Eve sees is K XOR dog. And Eve doesn't know which world that she is in. So let's go through and think what Eve should do in both worlds. Let's say we're in world number 0. If we're in world 0, M0 must be cat. So Eve knows that. And she knows the ciphertext because that's sent over the channel. So if she does a little bit of algebraic manipulation, she can see that K is equal to C, the thing that she received over the channel, XOR M0, which is cat. And that's the key. So if we're in world 0, and Eve knows that we're in world 0, she can derive this key. On the other hand, if we're in world number 1, using the exact same trick, Eve knows C, that's the ciphertext that was received. Eve knows M1, that's dog in this world. So she knows what the value of K is. It's the thing she got, XOR dog. So if Eve knows which world she is in, she can actually come up with the key for that world. Unfortunately, Eve doesn't know which world we are currently in. So it turns out Eve has to guess, am I in this world where K is this value? Or am I in this world where K is this value? And she doesn't know K. So both of these possible keys they're both possible, and Eve has no way of knowing which key was used. Both of these keys are plausible keys, and because we generated the key randomly, we could have the key from world 0, or we can have the key from world 1. We don't know. So in this case, Eve's strategy was to take the ciphertext, which is one of these two values, XOR it with cat, get one possible key, XOR it with dog, get the other possible key, and she's stuck. Both of these keys seem plausible. There's no way to tell which one is more likely than the other. So in other words, Eve has no idea which one was encrypted. Was it cat? Was it dog? We have no idea. Trying to figure out the key doesn't help us whatsoever because both of these keys are equally plausible. So this cute little security proof basically shows us that this scheme does not leak information. If Eve doesn't know the key and she receives either the encryption of cat or dog, she is no better at learning which one was encrypted. She gets no extra information about the key or which message was encrypted. Both of these worlds are equally plausible. So this is the little security proof that shows why one-time pads provide perfect security under certain constraints that we will see.